So I'm not going to state the title. Basically, there's a lot of emerging hardware technologies that promise to revolutionize computation. They offer benefits such as improved performance and energy consumption. They offer higher storage densities and faster memory access times. And at the limit, they offer new kinds of architectural capabilities, such as the ability to implement dense 3D interconnect and to have chips that are both vertically and horizontally laid out. Now, of course, these emerging hardware technologies have their growing pains. Even though they're highly promising, they're much less reliable than conventional memory and compute substrates, such as CMOS and DRAM, and they occasionally corrupt bits. These bit corruptions might arise for a variety of reasons related to fabrication, the material properties, and to sensitivities in the environment. Now, of course, the issue is when you're trying to perform classical computation on these hardware substrates, we run into problems because where corruptions occur in the program and in the program data has a substantial impact on the computed result. Namely, in classical computation, we are highly sensitive to bit corruptions if the wrong bits are corrupted in our computation, right? And so, of course, over the years, there's been a number of error mitigation techniques that have been developed to work around this problem, but these error mitigation techniques come at a cost, right? They introduce hardware complexities and hardware and software overheads that might affect the projected energy and performance benefits and might just not be implementable in this new class of technologies. So what else can you do? Well, what we can do actually is we can change how we do computation. And that is where hyperdimensional computation comes in. It is a computational paradigm that actually comes from the cognitive science community that is extremely error resilient. You can think of it as a mixture between a code and then a cognitive science primitive. The basic unit of information in hyperdimensional computation is a hypervector, which is a high-dimensional binary vector. In HD computing, information is actually evenly distributed across bits. So each bit is equally useful or useless to your computation. What this means is you can corrupt a bit at any position in your hypervector, both during compute and in storage, and it will have the same effect on your computation. The second characteristic of HD computing is that we only care about distances between vectors, namely the Hamming distance between vectors. And what that means is that you actually need many bit corruptions to occur to make two hypervectors that are far apart close together. And what that means is you end up with a highly error resilient computing paradigm. You can implement many different things with hyperdimensional computation. We'll be focusing on data structures, hyperdimensional computing-based data structures in this talk, but you can also implement a variety of processing tasks, and at the extreme, you can actually implement machine learning models. So our work is the first static analysis-based optimizer for optimizing hyperdimensional computations to execute with acceptable accuracy on emerging hardware technologies. Right. So we present basically the first static analysis that lets you optimize these computations. Our static analysis provides accuracy guarantees over all data structures and queries that are captured by a program specification while minimizing resource usage. And as I mentioned before, it is static, which means this analysis completes in milliseconds at compile time. The second characteristic of this analysis is that it's actually hardware aware, and it's able to optimize computations to execute accurately on emerging hardware technologies. Unfortunately, I cannot really tell you about the analysis unless you understand how the computing paradigm works. So we're going to cover the computing paradigm and the analysis and the results in the next 12 minutes. So wish me luck. And the best way to cover the computing paradigm is by example. I'm going to describe how you construct a graph with hyperdimensional computing. We're going to be working with this knowledge graph data structure. It is a directed graph with labeled edges and nodes. We will refer to node labels as concepts, edge labels as relations, and edge directions as interactions. And typically what we want to do with this data structure is we want to query edges. And that's because edge queries, when you query an edge, you basically are able to ask about a relationship between concepts. For example, if you look for an edge that is flowing into the apples concept, the likes relation, you are basically asking the question, how many individuals like apples? Okay, and so to make things a little bit hairier, we want to actually execute this query on a piece of hardware that stores information in a 2-bit per cell resistive memory array. This is an information-dense emerging memory technology that is prone to error. The specific memory array that we characterize has an error rate of 2.15%. So you have a 2% chance of your bits getting corrupted. Okay, so how do we encode this data structure using HD computing? Well, first off, we need to make the atomic elements of our graph. So we're going to build a set of primitives or atomics to build graphs out of. Our atomics are the set of relations, the set of edge labels, right? The set of node labels, and also the directionality of the graph, or the directionality of an edge. When an edge is incoming, it's going to be a target edge, and when an edge is outgoing, it's going to be act edge. And so edges are encoded with relative to a node. Okay, so how do we do this? It's actually quite simple. We generate a random binary vector, which we're going to call an atomic hypervector for each type of node, label, and edge direction in our knowledge graph. So every primitive, every atomic in our data structure is going to become a random vector. And you might notice that if you take any two of these atomic hypervectors and you compute the Hamming distance between them, that Hamming distance will be large, which actually conceptually makes sense because the Apple node is not at all similar to the Plays edge. And so basically, similarity and dissimilarity between hypervectors capture similarities and dissimilarities in your data structure. Okay, and so now we're ready to encode a data structure as a hypervector using hyperdimensional computing. And the way we're going to be doing this is we're going to be going from the bottom up. We'll construct a hypervector representation of an edge, and then we'll use the hypervector representation of edges to construct an edge set, and then finally we'll construct a graph. Okay, so how do you actually encode information? Well, it's interesting. What you do in HD computing is you actually compute over your atomic hypervectors to embed information about your data structure. Okay, so let's start with edges. Let's say we want to construct a label-directed edge relative to a particular node. And we're going to focus on this edge right here. So relative to the Mary node, this edge originates from the Jack node, has a likes label, and it's going to be flowing into the Mary node, so it's a target. So you can actually think of this as a tuple, target, likes, Jack, right, within the context of the Mary node. How do you encode this with HD computing? Well, what you do is you take your target, likes, and Jack atomic hypervectors, and you bind them together. A binding operation is actually a simple bitwise XOR, and what it does conceptually is it creates a hypervector that is dissimilar to its inputs. So that means if I take that HV1 hypervector and I compute the Hamming distance between that hypervector and the target atomic, the distance will be large. Same thing will hold for the likes hypervector and the Jack hypervector. Okay, so basically what we do is for every edge hypervector that is connected to Mary, we're going to construct our for each edge that's connected to Mary, we're going to construct a edge hypervector that encodes the tuple, right? So we repeat this process 3 times. And now what we want to do actually is we want to group these edges together, right? We want to create a set of edges that contains all of the edges that are connected to the Mary node, right? And so how do we create a set of edges? What we do is we bundle the hypervectors together. A bundling operation is implemented with a bitwise majority, and what it does conceptually is it creates a hypervector that is similar to the input hypervectors, right? Which means that when you bundle together this edge hypervector, and this edge hypervector, you again get another hypervector. But if you compute the Hamming distance between HV Mary and HV1, for example, you will find the distance is small. Same thing will hold for HV2 and HV3. And the interesting thing with this property is now you can actually use the Hamming distance to perform data structure queries. So now we can, for example, test if an edge is contained within an edge set by computing the Hamming distance between the hypervector encoding of an edge and our edge set hypervector representation. If the Hamming distance is small, the edge is in the set. And if the hypervector distance is large, the edge is not in the set, right? So now we can do set membership. Now what we do is we build an edge set hypervector for each node in the graph. So we end up with this collection of hypervectors per node. And now at this point, we basically have encoded our graph data structure, right? We have like a table of nodes and then edge sets. Now let's see what happened. Now let's walk through how you actually execute a query on this graph. Well, again, we're going to pick on this likes apples edge query. So we're going to specifically look for an edge that is flowing into Apple with a likes label. So it's an incoming edge with a likes label that's flowing into Apple. And you can, of course, represent this by binding together act, likes, and Apple. So how do we do this query? We compute the Hamming distance between our query hypervector and each of the edge sets that we've just built in our data structure. And then we basically compare the Hamming distance to some distance threshold. If the distance is small, the edge is contained within the set and therefore connected to that node. And if the distance is large, then it is not contained within that set. Make sense? All right, so you might notice that I've very conveniently left out some information. You might be wondering, how do I tell if a distance is small or large? Well, the answer is you need a distance threshold. And that is another quantity you need in this computational paradigm. And the other thing I left out is I didn't tell you how big these hypervectors were, right? And so you might ask, well, how do I make these decisions? Well, the answer was, at least before our work, was that you would do dynamic tuning. So you would do a bunch of Monte Carlo simulation over a set of test inputs, and you would try to find some size and some threshold that gives you the accuracy that you want. Obviously, this approach has problems. You're not going to get any accuracy guarantees. It might not generalize well. You can, for example, construct a graph that looks very similar to the graphs you tested on, and it might give you a much worse recall accuracy. And the other issue is it's computationally intensive. Your inner loop is Monte Carlo simulation, and then you're doing a parameter search on the outer loops. Okay, so as I mentioned before, our work is the first static optimization technique that basically is a static optimizer, and what it does is it analytically derives the minimum hypervector size you need for a computation and the distance thresholds you need to use to execute your queries accurately. Okay, so now we can take a little bit of a closer look. So Heim takes as input a specification of the program to optimize. This program specification describes the space of HD data structures to analyze and also specifies the desired query accuracies. Heim will compute a hypervector size and a set of distance thresholds that satisfy all the query accuracy constraints in your spec. This particular constraint basically asks Heim to make sure that edge queries on our knowledge graph data structure execute with 99% accuracy. So to be a little bit more precise, Heim's accuracy guarantee promises that on expectation, the accuracy of each described query will converge to the accuracy specified by the most restrictive accuracy constraint describing that query. And so you basically get, it'll converge to that accuracy, right? It's not a gross over approximation or anything. And then Heim additionally ensures that this accuracy guarantee will hold over all the queries and data structures that are described in the Heim specification. And so, for example, in this spec, the data structure that is described is all graphs with a maximum cardinality of 4. And the kind of queries that are captured are all edge queries within these graphs. And so basically, as long as you follow these rules, the accuracy guarantee will hold. Heim also accepts a hardware specification, which specifies the bit error rates of different storage and compute elements in your hardware architecture. Heim's accuracy guarantees hold in the presence of hardware error. And you might notice I also mentioned compute. You can also have error occur in your computational, during computation, and the analysis will also handle that. So it's not just on data. And so what Heim produces as output is it analytically derives a set of optimal distance thresholds and a minimum hypervector size, and it produces those parametrizations as output. And in fact, it also produces additional hypervector sizes per query, and you can actually use these sizes to do partial computation soundly, which is pretty fun. Okay, so now we can look at the guts. Those are the inputs and the outputs to Heim. So what do the internals of Heim look like? So Heim's implementation consists of an analytical model of the hypervector query Hamming distance distribution for a given data structure. And this distribution is actually parameterized over the size of your hypervector. So you can feed in different sizes, and you can figure out what your distribution of distances will look like. This analytical model is fed into an accuracy analysis, which analytically derives the query accuracies for the given analytical model. And then finally, we have an optimization algorithm that uses the accuracy analysis to find the smallest hypervector size that meets the accuracy constraints that are provided. And you can just do this, this can be done with a binary search. And so we'll take a little bit of a closer look at the analytical model. That's a lot of the technical meat of our paper. The analytical model precisely models the distribution of Hamming distance for matching data structure queries and non-matching data structure queries. The reason why we observe distance distributions is because there's non-determinism introduced when you sample those atomic hypervectors and when you introduce hardware errors. And as you might have noticed, these distributions are normally distributed. And what we do is we actually derive the closed form formulas for the mean and variance of matching and non-matching queries parameterized over hypervector size. These formulas, the structure of these formulas are of course also predicated on the expression structure. So we have many subcases that we've derived that apply to different expression patterns. And then to model hardware error, basically we compute the upper bound of the bit flip probability, and it's actually, you can very naturally fold this into the mean distance model that is used by our analysis. And then, of course, once you have that analytical model, you want to perform an accuracy analysis. We also are able to derive closed-form formulas of the expected accuracy, and then to use for this analysis. And then we're able to use the CDF of these formulae, or we're able to use this formula to derive an optimal threshold. So to develop this analysis, we apply results from the theoretical cognitive science community, and we also contribute new derivations. How does Heim perform? So we evaluate Heim on 5 different data structures where we use 5 parameterizations for each data structure. And we compare Heim against dynamic tuning. And we configure both approaches to try to target 99% accuracy on the query, on being able to recover information. So comparing runtimes, Heim runs in milliseconds and is 2 to 5 times orders of magnitude faster than dynamic tuning. And as you can see, the runtime is flat, so it does not depend on the data structure size, which you would expect because these are all closed-form statistical models. Heim also is able to much more reliably give you the accuracy that you want. To evaluate this, we sampled 100 random data structures that were conformed to spec, and we evaluated dynamic tuning and Heim on these data structures. As you can see, all of the Heim data structures, which are in blue, are above the dotted line, which means they satisfy the accuracy requirement. And then, as you can see, the dynamic tuning is under the gray line in a lot of these benchmarks, which means that once you try to generalize it to other data, generalize the parameterization to other data structures, you no longer get accurate recall. And you can see in some cases you never actually meet the accuracy that you want. One more point I'd like to make. One of the cool things with this sort of analysis is that you can actually do applications to devices co-optimization. And this lets you do ISO accuracy analyses of different hardware technologies. For example, we evaluated whether it's ever beneficial to use 3 bits per cell memory versus 2 bits per cell memory versus conventional memory. And we found that at ISO accuracy, 3 bits per cell resistive RAM is worse than DRAM. But 2 bits per cell ReRAM is actually, the storage benefits are not eclipsed, right, by the amount of additional bits you have to consume to retain a specific accuracy requirement. So anyway, the neat thing here is you can do systematic applications to devices analysis, which is typically very, very hard to do with classical programs. And that is it. I will take questions.
Yeah, questions? Please represent your question as a bit vector.
Will be difficult. Thanks a lot. I found the maps very cool. I wonder if you have tried to benchmark this kind of hyperdimensional computations against a traditional approach, because it's not totally obvious that good old error correcting code with known algorithm in the task vectors.
So you're asking about the comparison with ECC, is that right? Like error correcting codes. Okay, so yeah, the thing with ECC is that it works when you want to just store data, right? You encode your data, you store it, and then you decode it. But then you still have the decoding operation. Your computational path still has to be accurate, right? With this, you never actually decode your data. So you can actually just keep operating over the hypervectors on the data path and experience corruptions and be fine. Does that make sense? So it's a little bit different, but actually...
I was thinking runtime, how does it compare in terms of performance?
Okay, yeah, we might take this question offline because I think the next speaker has to go up, but, right?
You can just take the laptop off and then...
Okay, got it. Yeah, so to do that, you'd have to compare ECC and redundant computation, right? I don't think anyone's actually done this comparison. I should also mention this computing paradigm has only been used practically for the past 2 years. So there's obviously a lot of work still to do with these comparison points. I would also like to add that data structures are not really where we want to target our end goal, right? We want to actually target some of the ML use cases. So,
Okay.
And I'll take questions after the session.
All right, let's thank our speaker one more time.